I'll figure that out. If your DAC was a 1 microsecond DAC, it could do the conversion completely in 1 microsecond. And you had a 16-bit converter that's over 65,000 individual comparisons. So it would be 65,000 microseconds or 65 milliseconds. Ugh. So, that's great if what you're trying to digitize is a 5 hertz signal, but it's not going to work for audio. That's for darn sure. But there is a very simple upgrade to this. And that upgrade is to use, instead of an up counter, we use a successive approximation register, an SAR. Now, what that essentially does is it produces a series of values. Instead of just going from 0 up, it produces a set of values bitwise working from MSB down to LSB. So the very first value that it's going to produce, we're going to sort of set this up like yay, right? Top nibble, bottom nibble. Very first value it's going to produce is this. So it's halfway up, okay? Now the comparator output's either going to be high or low. If the comparator is telling you that the input signal is bigger than this, then I know this must be a 1. And now the question is, what's this bit? So it'll set this to a 1 and see if the input is still bigger. If it is, it'll go on to the next one. Now, if it's not, in other words, if 1, 1, 0, 0, 0, 0, 0, 0 is higher than the input, then we'll simply reset this back to 0. Go to the next bit. So what we do here is number of comparisons is n. Oh, that's way better, rather than 2 to the n. If I have a 16-bit converter, that's only 16 comparisons. So this thing is way fast compared to using an up counter. This is kind of like, there's a little parlor trick you can do, which is you can tell someone, hey, think of a number from 1 to 1,000. Don't tell me the number. I'll bet you I can guess this number in 10 guesses. All you have to do is tell me whether my guess, each guess, is higher or lower than your actual value. So your first guess is going to be 500, right? So let's say that, the person's original value is 400, just to throw a number out there. So he says, oh, you're too big. Oh, great. Right there, I've already thrown away 500 possible values, right? From 500 up to 1,000. They're gone, they're history. So now I cut it in half again and I say, well, 250. Now the person says, oh, that's too small. Okay, great. So there's no worry about anything below 250. I know the value is in between these two. So I'll guess 375. And they say, oh, they're still too small. Great. So now I know it's between 375 and 400. Right? I'll split the difference again so that that value keeps getting smaller and smaller and smaller. You can see, within a very short period, I've really narrowed down, and in just 3 guesses, I know the value has to be somewhere between 500 and 375. And this is just going to keep on going, okay? And in fact, we will get it in 10 guesses. Why? Because 2 to the 10th is 1,024. You're basically doing this. Every time they say you're high, you're low, you're basically setting or clearing one of these bits. We say 1 to 1,000, 10 guesses. It sounds like, oh, this is really nice. Geez, 10 out of 1,000, that's only 1%. Yeah, sure, I'll give you odds on that. No, you're crazy, right? This little sort of binary search is guaranteed to work, right? So this turns out to be a very simple kind of technique that's relatively fast. Not as fast as a flash, but it's still relatively fast, and you can have modest circuitry. Downside, what if the input signal changes while you're doing this? Well, right there, we're probably going to put in something called a track and hold amplifier. Basically, it locks onto the input signal. In the old days, we used to call these sample hold amplifiers. But basically, it just clamps onto the signal. So that way you can do this while the input signal is actually changing. Right. Also, we're going to make sure that we have to have up front here an anti-aliasing filter. Don't forget that, right? We need an anti-alias filter. So, the F2 there has to be somewhat less than the sampling frequency divided by 2. Another possibility, which I'm not going to discuss here, but for very high resolution converters, we now use a technique called delta sigma. Sometimes it's called sigma delta. This is a very, very high speed oversampling technique where we end up with a whole bunch of samples of low resolution. And then we go through a process called decimation, where we take this sort of pool of low quality samples, if you will, low resolution samples, and through a mathematical process, we can derive one high resolution sample. So this thing might be oversampling by, a factor of 256 or something like that, compared to the Nyquist-Shannon sampling rate. So that's something else that we'll see, right? But that gives you a pretty good idea of what's out there and what we're going to do.
Get a fresh start to the new year and connect fast.
Sir, remember you're still muted, sir. In case you're saying something to us.
All right. I am now saying something to you. All right. Let me see. Anybody understood anything? What's happening now? Just now?
Yes, sir. What I don't understand, sir, is how exactly the SAR works, sir. Is it just like
You're a little low.
works
You're a
just how
little
it
low.
was described?
You're a little low, Mr.
Oh,
Vassar.
sorry. What? The only thing I don't entirely understand, sir, is how the SAR works. Is it just like it cuts the number in half every single time until it gets to that number, or is it like something different than that?
Well, it's a former.
Okay.
1 second. Let me remove this. All right. You guys are seeing my screen as well?
Yes, sir.
Okay.
Yes,
All
sir.
right. Let's go through the easier method. All right. That method basically was showing you how to use comparators, pretty much how to use comparators to convert analog signal to a digital signal, which pretty much what it does is that, okay, if you guys recall what a comparator does, it has two inputs, and what you do is that you apply input signal, of course, to the non-inverting input, and put a reference signal on the inverting input. And then what you do is that you compare the signal, and if the signal is greater than a certain value, then it would make a determination that that value that is currently on that particular comparator is either a 1 or a 0. Because remember, that's what we're doing. We're trying to find out whether or not the information is either a 1 or a 0. So we have an analog signal coming in. You sample analog signal at a particular instant in time. That instant in time, that value, you're going to determine whether or not that value that was sampled is greater than a certain reference point. So you're going to set the reference point using your inverting input. If the value is greater than a certain than the reference, it's going to determine that that value is a logic 1 or a logic 0. Basically, you follow that?
Yes, sir.
Yes, sir.
Okay. All right, so let's look at what we have in terms of what I spend time writing. Although some of you guys, of course, say that my writing is a lot of crap too. So let's look at a crap too for a little while. Okay, here we go. So let's go straight to the analog to digital converter. Analog to digital converter, and I'm starting right here because we basically saw what a digital to analog converter was, and we're going to look at two examples and we're going to move on quickly. So let's just read and try to conceptualize at the same time. So analog to digital converter is a common interfacing process often used when a linear analog system must provide input to a digital system. The simultaneous or flash method of analog to digital conversion uses parallel comparators to compare the linear input signal with the various reference voltage developed by a voltage divider system, or voltage divider. When the input voltage exceeds the reference voltage for a given comparator, a high level is produced on the comparator's output. The figure below shows an analog to digital converter that produces 3-digit binary numbers on its output, which represents the values of the analog input voltage at its changes. This comparator requires 7. This converter requires 7 comparators. Anybody can tell me why? Why would you need 7 comparators?
2 to the n-1, sir. N being the number of bits you require.
Okay. How much we need? How many bits?
3, sir.
Okay, so it's a 3-bit. So 2 to the 3 is what?
Isn't 2 to 3?
8.
8, sir.
Okay, so 8 minus 1.
7.
All right. So you see why we need 7 comparators, right? Is there anybody who I don't understand how we get there?
Sir, wouldn't that be 2 to the n-1?
If it's 2 to the n-1, that's what you said?
Yes, sir.
Yeah, that's what the person said as well, or whoever said, right?
I thought you said 2 to the n. Oh, sorry.
All right. In general, 2 to the n-1 comparators are required for conversion of an n-digit binary number. So if we know that we need a 4-bit binary number, N will of course be
4.
4, right? So it'll be 2 to the 4 minus 1, and that tells you how many comparators you would need in the conversion process. All right?
Yes, sir.
Good. The large number of comparators necessary for a reassemble size binary number is one of the drawback of the simultaneous analog to digital converter. The chief advantage, however, though, and they spoke about it in the video, is it is able to produce a fast conversion, right? So in terms of, and that's why they call it flash. So this is the circuit. We said that we wanted a 3-bit binary number, right? So we need to have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 comparators. And by now we should all know how comparators work. Yeah?
Yes, sir.
Good. Beautiful.
Yes, yes, sir.
All right. So look at the circuit properly. Notice something. That our input is an analog input. So we have an analog input voltage, right? And that analog input voltage, remember we always say that the input voltage to be compared is always applied to what? The non-inverting input, right? Of a comparator. So you notice the input voltage, it has been applied to the non-inverting input of the 7 converters. For 7 comparators. Whilst, what goes on the inverting input?
The reference voltage.
Our reference voltage. So our reference voltage is what we're applying here. But what we do is use resistors, what is called weighted resistors. We use resistors to give us different voltage for each comparator input. So here we're applying VREF. But the difference between the voltage that is going here and the difference that is going to go here as a reference voltage is going to be the voltage divided between these resistors. You follow me?
Yes, sir.
And likewise, the continuous and continuous right down there. So
Sir.
Yes?
Sir, the resistor value, right, sir?
Mm-hmm.
Is like different resistor values are put in, or the resistors are the same value?
All right, let's discover that by the further reading.
All right, sir.
The reference voltage for each comparator is set by the resistive voltage divider circuit and RF. So RF, which you know is where you start your reference voltage, right? So you have a reference voltage, and that voltage is going to be continuously being divided as you go down from comparator 1 up top to comparator 7 in this case. The output of each comparator is connected to an input of the priority encoder. So again, look at the diagram. Notice something? We have how many inputs? 8 inputs, starting with 0 being the grounded. Because you're not going to get, if you don't want any voltage on this, it's going to be grounded, right?
Yes, sir.
And then we have from 1 to 7, which gives us 1, 2, 3, 4, 5, 6, 7, 8 inputs, right? But we're going to get a different voltage coming out of each of these comparators based on the reference voltage that is applied and what is being compared. And as I said before, each reference voltage for each comparator is going to be different based on the weighted resistors. All right, let's just go a little further. The priority encoder is a digital device that produces a binary number representing the highest value inputs. So let's go back again here. So this is the input, for example, this is the input that is coming to input 3. The input, it's going to represent the highest possible number that, so what's the highest number? Because of course, it's 3, it's going to be, the highest possible is going to be?
You
3,
mean
right? Right,
Ah,
which in this
that's it.
good. So what I'm saying is that each of these really represent the equivalent voltage that is going to come into the comparator. And the comparator is going to recognize that based on the value that comes on each of these respective input, it is going to know what output value it is supposed to be outputting right here. Because remember now, this can go from what? 0, 0, 0, the output, to 1, 1, 1. What does that represent? It represents, as we know, from 0 to 7. All right. Based on what we would have known in terms of logics, right? Digital circuits plus just general logical conversion that you would have and probably done before. So the encoder samples, the encoder samples its input. So what the encoder is doing now is checking its input. When a pulse occurs on the enable line, so if you notice, the encoder has what is called enable line. So when the enable line is active, what it does is check all the input and see, okay, which one of the input actually has a signal, And then based on which one of the input has a signal, it converts a signal value and put it to the output. So the encoder again is like the gateway. Before anything is passed from input of the encoder to the output of the encoder, the enable is what checks these and make that passage based on what is available at its input. Okay? So, where am I again? All right, the encoder samples its input when a pulse occurs on the enable line, right? And a 3-digit binary number proportional to the value of the analog input signal appears on the encoder's output. The sample rate determines the accuracy with which the sequence of the binary number represents the changing input signal. In other words, it's an encoder that's gonna, it's an enabler rather. The enable that's gonna determine how quickly it actually samples or glet what is on the input of the party encoder passes to the output of the party encoder. All right, so here, for example, if you did not fully understand, we use an example to illustrate the basic operation of the analog to digital converters. Example. So here it is that we have an analog signal, agree? So this is our analog signal that we have. And in this case, a nice-ish looking analog signal. And you must determine the binary number sequence of the 3-bit simultaneous analog to digital converter for the input signal that is applied. So this is your input signal, right?
Yes, sir. Yes, sir.
Good. This is the encoder enable pulse. In other words, this pulse is what's going to be right here. This is what's going to determine when each of the value that comes in here is checked and passed to the output. So if you look at this, what's happening is for the first pulse, or for the first, when the enable is on, what it does is go boom, it checks. So for here, let's say that the enable was high, a high enable. So it means on the rising edge, it will check the pulse. It will check the signal, the analog signal, and see what value that is. So it goes up here, it checks the value. You see that, for example, in this case, it would be seeing what number it would be seeing here for the first one. Increase the size. For the first one, what value would it be seeing?
2, sir.
All right. Somebody said 2. That's fair enough. You guys can see. You guys can see, right? So here's here's what I'm saying. If it's
Wait,
if
sir,
it's
no, go ahead.
okay. So this is your input. This is a signal that is being inputted. Good?
Yes, sir.
When the signal is inputted, the signal is going to be the inputted signal that is going whoop, whoop, whoop. Right? That's the input signal that's coming in here. The input signal is going to be compared. So that the input signal is going to be compared to the reference voltage. Because of the resistor value, what you'll find is that the reference voltage gets smaller and smaller and smaller as you go down. You realize that? So this is the reference voltage initially, and that is going to be divided. That's going to be, it's going to get smaller. And then we divide it again, it's going to get smaller, it's going to get smaller, it's going to get smaller based on the resistor values, right?
Yes, sir.
So it means that the largest value, yeah, is going to be the largest value that is going to be compared is going to be the top comparator in this case. So let's say the signal goes and it checks, and when the signal goes in, the comparator compares and it say, okay, based on the resistor value, the voltage that is going in as a reference is 7. And then it says, is the input signal 7? And if the input signal is not 7, what's going to happen? Here, what's going to happen here?
Sir, got output a low.
A 0.
Yeah, it's going to output a low. You get in the picture now? And it goes and it say, okay, all right, the next one, because of the weighted resistor, I say, okay, this one is what is going here. The signal that is coming here is the same input signal, but in this case, the input signal is 6. And let's say the input signal, you're sampling the input signal each time, right?
Yes, sir.
And what it is doing is that every time the input signal that is coming in at each interval in time is going to be compared. But because of the rated value of the resistor, it's going to determine whether or not that reference voltage, based on the resistors, the voltage divider of the resistor, that voltage is going to be greater than or less than the reference voltage. And so they're going to put a 0 or a 1. You follow me? It's going to put a 0. Because remember, what's coming out here now is going to be a maximum. Again, because it's a comparator, it's going to be either it's greater than the reference or it's less than the reference. So if it's greater than the reference, and let's say the reference is 7, it's going to say, okay, the signal is greater than 7 right here. Or it's less than 7. And if it's less than 7, it means that when the enable is applied, it checks this one, it sees that it's less than 7. Say, okay, that's not gonna give any output value here, eh? So in other words, it's gonna output a 0 for this one. It checks this one, it sees that it's a 0. It checks this one, it sees that it's a 0 because it's less than, right? But when it checks this one, it sees that the voltage that is outputted from this comparator, when the two signal, the reference signal and the input signal are compared, that input signal is greater than the reference signal. So it output a positive value here, right? Then when it output a positive value here, when that is checked, based on the enable, it's going to say, okay, what we saw a value that is greater than 4, but of course it's less than 5. So it's going to give you a 4 for that. Yeah? Right? You understand me? And then that's going to now produce, it's an encoder, you know? So remember what the encoder does? Is convert that signal that it would have gotten to ones and zero, code it to ones and zero, right? So
Yes,
that's
sir.
what's right. So that's what's
Sir,
happening here.
Theodore has a question, sir.
Who? Go ahead with the question.
Oh, it looked like it was a mistake. Never mind. Continue, sir.
Okay.
No,
Right.
actually,
Go ahead with the question if you have a question.
sorry, you said that if it's a 4 isn't 4 less than 7?
Okay.
Because you said when you have a value smaller than the number, you output a 0 or a low.
Remember how the comparators work. So let's go through it slowly. This is the signal that is coming in. The signal that is coming in right here. So that this signal is going right here. Okay. When the signal comes in, based on the value of the signal, so the signal is going to be divided up into intervals of time, eh? So at each interval of time, when that signal goes in, yeah, that signal is going to be compared to the signal that the reference voltage that comes on here. If at this interval in time, let's say this interval in time, the comparison is being made, and the signal voltage right here is, say, let's say 3. Okay. So right here, because it starts at 0, goes up, 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 up. So when it does it, right at this point, this voltage is compared. When it's compared here to the reference voltage, if the reference voltage, yeah, based on the resistor value, is saying, okay, is realizing that this input voltage that is coming right here, now at this point is 3. It's 3. And the reference voltage at that time based on the resistor is saying that this is 6, for argument's sake, 6 volts. What does the comparator do again?
It checks to see if there's a difference between them, then
Right. It compares both inputs. If the input signal, remember this from a comparator, that's how we did it before. If the input signal is less than the reference signal, remember what's going to happen? The output of the comparator is going to be driven into negative saturation. Remember that?
Yes, so it's going to amplify a negative.
Yeah, it's going to be driven. The amplification is what's caused it to be driven into negative saturation. So it tells you right away, because it has been driven to negative saturation, that the voltage, the reference voltage, is greater than the input voltage. So be that as it may, that comes here and it says, okay, when the enable sample, it realizes that on this line, there is not really a voltage because the reference voltage is greater than the input voltage. So it's going to say, okay, there's nothing here, which makes sense because it is looking for, let's say for 7 volts, and I'm just using this rule. It's looking for 7 or greater. Sorry, it's looking for a 6 voltage rather, or greater, right? And if it sees that it is less, it's going to be, as far as I'm concerned, 0. Nothing's going to be coming in. If this voltage at the same, because remember, I know the input voltage is going to be the same at all time. So again, for this one, it's going to be 3 again. At that instant in time, it's going to be 3 again, 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 it's going to be 3 again. So each of the comparisons are going to be made against the reference. And if it finds that the reference is actually greater than the input voltage, it's going to be driven into negative saturation. However, when it finds that the input signal that's upset. And when it does the comparison, it sees that it is greater, then it actually put a positive voltage on each of these inputs. When the enable check and see that there's a positive voltage, it converts, it causes the enable to convert these positive voltage and give you a digital representation at the output. That's as simple as how it works. So let's go back again to the question. So be that as it may, this is your input voltage. When the input voltage is sampled, the enable check and say, okay, based on the particular comparator, this is what we're getting. So when it checks the and say, okay, because remember now the enable, then the encoder is operating using the enable input. And the enable input checks the signal that it has received from the comparator, from the outputs of each comparators. And when it checks, it realizes that at the particular instant in time, the input signal was less than these values up here, but it was greater than these values. So you check and you say, okay, if the input signal at this interval of time is say 3, let's say right here, then it is gonna tell the enable or the encoder rather to convert this value that it checks of 3 when it was encoded, when it was sampled right here. It was sampled and say, okay, it is a 3 because it realized that, remember how the encoder or the comparator works? It's gonna put out a voltage when the input voltage is compared to the reference voltage and it is high. Otherwise on that, these are going to be low. So as far as the concern, all the other comparators values above this point is going to be a 0. Because at this point, you see, there's no signal here. There's no signal here, only from here going down. So it's at that interval, it is 3. And of course, the encoder is going to give you a code for what the voltage that was sampled is. So it's going to give you, in this case, for 3, a 0, 1, 1. And continue the whole process. So if you should look at what I'm saying in terms of the solution, it says that this is the input signal, this is the enabled pulse that is checking the input of the encoder to give you an output. So here is the resulting binary output sequence is listed as follows and is shown in the waveform diagram of the figure below in relation to the sampling pulse. So again, remember what I just said. This is your encoder. The encoder samples, and when it samples, it finds that the value right here is 3. You know that this is your most significant bit. If we have a 3-bit, as I mentioned before, it's a 3-bit encoder. 3-bit encoder. So this would be D0, which is the least significant bit. This mega one would be D1, and this would be D2, which simply means 2 to the 0, 2 to the 1, and 2 to the 2. That's what these values are representing. So when we enable sample a signal that is coming to the comparator, it sees that this was the only value that was equal to a 3. Everything else above 3 would have been 0, right? So everything else, it finds, when it does the comparison, everything else is 0, meaning that the reference is greater than the signal. Only when it reaches here, it finds that the reference is equal to or less than the input. So it outputs something on this line. When it outputs something on this line, nothing else is outputted on these lines. So these are all zeros. So what happens is that then when it's that signal for the voltage of 3 based on the comparison is then sent on a binary representation for this value at the input of the encoder is going to be outputted here on D0, D1, D2. And if it was 3, then it means that this would have been a 1, this would have been a 1, and this would have been a 0. Because, of course, this is 2 to the 0, which is 2 to the 0 is 1. And then this is 2 to the 1, which is 2. So this would be a 1 plus a 2, which will give you a 3. So that's why you will get this value at the output of the encoder. So that's what happens right here. It is seen for the first sample a 3. So the 3 would be 1, 1, 0. For the second sample, it goes up here and it sees a 5. So right here, second sample, it is seeing a 5. So it's, when it sees a 5 for the input signal, it's gonna of course tell the encoder, say, okay, a 5 is what is coming out here, because when the comparison is done, it sees a 5 is greater than the reference, so it outputted a positive. But here it would be 0 because it's outputting a negative. So therefore, the highest value you have to convert, the highest value that you see in that number to the equivalent digital number. And 5, as we know, would have been a 1, 0, 1, which is what is done right here. See, for the second sample, it sees a 1, 0, 1. For the third enable pulse, third one, it goes and it samples and it sees 6. And I'm just using a guesstimation, right? It sees 6. And it's the same thing. It's going to convert that 6. It's going to see that the 6 is the one that comes out here, showing that this is greater when the comparison is done, right? This is going to be less, so that's not going to be. And even if these are going to give you high values, what it's saying is that you convert the highest value. That's what the prior encoder does. It converts the highest value that it would have gotten to its binary equivalent, right? So in this case, 6 would be a 1, 1, 0. And that's what is being represented here. That for the third pulse, it sees 1, 1, 0 as the highest. Any questions?
No, sir. It's pretty straightforward at the very least.
Absolutely, absolutely. Love to hear that. So that's all it's doing. That's how this analog to digital conversion is done using this very simple set of comparators. Just note, of course, the great disadvantage or drawback for it is, of course, you're using, based on the sample size, you're going to be using several comparators. But the good thing about it is that it does it very quickly. It does the conversion. It's what is called a flash or fast comparator. So it does it very, very quickly. Okay? So this is a flash comparator. Good. So that was what most of the time, that was what the SRM, the gentleman was saying, that inside that black box, that's where the comparison is being made. And then the digital representation is outputted in the video.
Sir?
Yes, sir.
Oh, sir, battery is about to die. That Sam just wanted to ask if will it be required that we know a specific conversion process, or will any of them work as long as we know how to apply it, or should we just be familiar with the flash process?
No, I'm just explaining to you how you actually achieve analog to digital conversion using remember using an operation amplifier. That's the genesis of our discussion, right? We've been looking at operation amplifier from the first class. And I'm showing you applications of operation amplifiers. We saw how it is used to apply to do several other things that we deduce and derive and analyze their particular equations. I'm showing you now that operation amplifier from last week can be used to do some other things and just to be theoretical in terms of coming up with analysis and equation. I'm showing you that in real world, you can have the operation amplifier being used to convert a sinusoidal wave to a square wave through the comparator. Show you how the comparator works. Now I'm showing you that also the operation amplifier can be used to convert digital signal to analog signals, as well as it can be used to convert analog signals to digital signals. And in this case, what it is showing you is that it uses this easy method called the flash or fast converter application. Of course, building on what we would have known and learned about comparators, using comparators to do this conversion. I'm teaching the concepts, so I'm not necessarily teaching and that you need to go and know this particular circuit. So if you should see another way of doing, and I'm sure based on I'm not sure exactly what Mr. Wright is doing and will be doing, but there are other ways. What we're trying to do here, Mr. Thompson, is showing you just real hardcore ways of doing the conversion or the application using operation amplifier. Operation amplifiers are so powerful that in the real world they can use to replace a lot of other circuitries that are in existence or have been used in the past. And again, based on the premise of the fact that operation amplifiers are built primarily in integrated circuits. You get in the gist? The operation amplifier being an integrated circuit, an integrated circuit be what they are, it means the size and power of things that you can use operation amplifier to build using integrated circuit are going to get smaller and smaller, and you can get all these functionalities or these applications using operation amplifier. That's what I'm trying to get at. Am I clear?
Yes, sir. So I think I'm going to have to be reviewing it a bit, sir, because I didn't put all of it together while you were talking, sir. But
that's why I have the notes. That's why I have the notes. All right? That's why we have the notes. All right. Any other question before we move on? All right. I can stop sharing that. And I can go back. to my. All right. Remember now. Don't worry. Anything you need to remind it of, it's going to be posted, and you can always ask. As a matter of fact, I should be the one asking you guys a lot of stuff. Because remember, you're supposed to be reviewing the things that have been posted. I don't like when you guys too silent though, because when you're too silent, I'm starting to wondering whether or not I'm talking to myself.
No, sir, there, man.
Okay.
Oh, talking about that, sir. At the end of class last week, sir, you said you were going to send us a video you wanted us to watch. You still have that video, sir?
What was that, Anna? What was I? Video
I can't. I think it was on offset voltage. Yeah, the same topic.
Okay.
You said you had a video you wanted to show us.
I think I did, but I didn't post it. I do, but I didn't post it to the group or the class, and I can do that afterward. But let's just look at this, and then the video will also help. You remember when we were talking previously? So we're looking at some. We look at some application of the operation amplifiers, right? But one of the things that we spoke briefly about when it just started was the fact that the operation amplifier, you can actually get an output voltage even though you did not apply an input voltage. We all discussed that, and we are knowledgeable about that at this time. Am I correct?
Yes, sir.
Yes, sir.
So the leakage inside of the transistors and so forth.
Right. Now, that is not necessarily a good thing. And one of the good things about the hardcore operation amplifier, the physical operation amplifier that are embedded in ICs, is that we have inputs that we can actually use to help to mitigate against this particular characteristic. That is not necessarily a good thing, because it's like, as I said before, it's like you start on a premise of uncertainty. You're applying an input voltage and expecting that the output voltage of the amplifier is going to be so and so based on its prescribed gain. Only to find out that when you actually measure the output is more than what you had expected it to be. Hence, it is throwing you off. So what do we do in a situation like that, especially when we require precision? We require things that really need to be giving us what we desire, especially when you're talking about creating certain applications. Certain things you want to be sure. You don't want to be sure plus or sure minus. You want to be sure that this is the case. Because especially with amplifiers, usually what happens is that they do have, they sometimes are buffers, or they're sometimes they're one, they're what is cascaded, and then one stage leads to another stage. And if you're actually having additional through 2-3 stages, at the end of the day, what you have is a false sense of security because of the fact that you have gotten offset voltages for each stages, which are going to be amplified and outputted and giving you a false output voltage as compared to what is expected, which can, of course, throw things off. So it means that we're going to have to now look at ways and means of how it is that we can actually account for these voltages, all right? So here, just the second paragraph in online. Everybody seeing my screen? I hope
Yes,
that
sir.
you see it's large enough. I know sometimes the ladies say that they're not seeing it. Are you seeing it, Miss Renee?
Yes, sir.
Okay. So the actual voltage of the actual value of the output voltage when the inputs are 0 is called the output offset voltage. Naturally, the output offset voltage is very much like a DC bias level in the output of a conventional amplifier, in that it is added to whatever signal variation occurs there. So you're adding something based on some variation. If an operational amplifier is used only for AC signal, it can be capacitor coupled if necessary, or desirable to block the DC component represented by the offset. However, the capacitor may have to be impractically large if low frequency and small impedance levels are involved. Also, a DC path must always be present between each input and ground to allow bias signal to flow. Small offset, on the other hand, small offset on the order of a few millivolts can often be ignored if the signal variation are large by comparison. On the other hand, a frequent application of operational amplifiers is in precise, high accuracy signal processing at low levels and low frequency. And in these situations, very small offsets are critical. So that's what I was talking about. You're gonna have a situation where you cannot ignore their offsetting condition, and by extension, you need to account for them. How do you account for them? Is dependent on a couple of things. One, your engineering skill set, and two, also what the manufacturer allows you to do. So here I said the manufacturer do not generally specify output offset because, as we shall see, the offset level depends on the closed loop gain. And remember when we created the closed loop gain networks, the gain of those closed loop gain and network is no longer dependent on the gain of the amplifier, which is what the manufacturer is creating, right? The manufacturer is creating the amplifier, the operational amplifier. And the manufacturer can tell you what the gain of the operational amplifier is. But when you place that operational amplifier in a certain network configuration, by now you would realize that the gain of these networks are no longer dependent on the gain of the amplifier, but it is dependent more so on the components that are used to design the network that you're using the operational amplifier in. We have done so many of these that by now you should see. We did the inverting, the non-inverting, we did the difference, summing, integrated, differentiated, all of these type of amplifiers, and realize that you're not looking at the gain of the amplifier anymore, but you're looking at the gain of the network that these amplifiers are a part of. Am I correct?
Yes.
Cool. So the manufacturers, that's why it says here that the manufacturers do not generally specify the output offset, because you realize that the output offset voltage is going to be dependent on your application of the network that you have, right?
Yes, sir. Sorry, sir. I'm writing same time.
Good. So as we shall see, the offset level depends on the closed loop gain that a user designed through the choice of external component values. So the manufacturers are not telling you what component values or what circuit you're supposed to use. They're created op amp. They're just creating their op amp and telling you the specific of their op amp. And you're going to use their op amp to give you the particular circuitry or the network that you want based on the functionality that you want it to do. So that's why it's kind of difficult for them to specify clearly that the offset output voltage for the operational amplifier is X. They'll give you certain basic things to look out for, right? So,
Sir,
yes.
sir, so does that mean, for example, if we use as one circuit and then we use two different op amps, we could get a different offset current, or would the offset current?
Absolutely.
Okay.
Absolutely. It's just like you use two different operational amplifiers. You will get two different gains based on what the manufacturer specified, right?
Yes, sir. Yes, sir.
Good. So what a manufacturer will do instead, it says here, instead, the input offset are specified and the designer can use these values to compute the output offset that result in a particular application. Is that clear?
Yes, sir.
Yes, sir.
Good. So in other words, the manufacturer say, okay, I don't know what kind of application you're going to use this thing, but these are the input offset condition. In other words, these are the things that they can do at the input in order to negate what you're going to get at the output when there's no input voltage, when there's no input signal applied. But as to what you're going to get at the output, we cannot tell you. That depends on your application. So the manufacturer specification sheet will tell you some generic properties to include the input offset condition. So here it says that the output offset voltage are as a result of two distinct input phenomena. One, the input bias current and the input offset voltage. And note these two terms carefully. The input bias current and the input offset voltage. And remember, I said that these are the things that the manufacturer can control. That's what they will tell you, right? We will use the superposition principle to determine the contribution of each of these input effects to the output offset voltage. So now we know two things. Two things that can affect the output offset. And that's what we're trying to limit, right? The output offset. But if we can do it from the input, it makes our life better because the manufacturer will tell us what these things are. Follow with me?
Yes, sir.
All right. So let's look at the input offset current as the first characteristic. All right.
You mean
The input offset current.
okay.
Good. In our discussion of differential amplifier circuits, we ignored the base current because they had negligible effects on the kind of computation that held our interests. All right, let's see what I mean. We know that some DC bias current must flow when a transistor is properly biased. And everybody say amen, because that's something that we should know by now, right?
Preach, Pastor.
Yeah.
Good. And I say this to say, because of the fact that I went through this with my students, some extent in semester one or devices one, I'm saying this. So Miss Renee, I know that you did not do this with me. So if there are clarifications, you can, and if you hear me speaking things that are not necessarily something that you are okay with, please free to let me know, okay?
All right, sir. Thank you.
All right. And that goes for the others, even though some of you or all of you would generally would have done this with me before. But we don't know this thing going on. Learn on to pass on the course and then remember anything at all. You know.
Is no sir?
I say we know that some people just learn to pass, learn the things and pass the course, and then sometimes they don't remember a thing. So we know how this thing goes. So if there are questions, please feel free to ask our clarifications. So we know that some DC bias current must flow when a transistor is properly biased. And although small, this current flows through the external resistor in an amplifier circuit and produce a DC input voltage that in turn creates an output offset. That we spoke about a lot to the point where we say, okay, when you have just the creation of the amplifier, the junction potential is as a result of movements of electrons in terms of electrons being attracted to holes, and current will flow even when we do not or have not biased the transistor. And then of course you're going to have a junction potential, and that junction potential has to be overcome through proper biasing for you to forward or reverse, forward bias the diode, and if you have the transistor junction, and if not, it will not be forward biased. That we do know. But look at what happens when these little currents are moving, creating an input voltage. That input voltage, as mentioned before, inside of the transistor is going to be amplified, especially if it's an operational amplifier, and it's going to be outputted. And therefore, even without a voltage being applied to the input, there is an output voltage. And that voltage, of course, is what we call an offset voltage. That's what this is trying to say right here. Now, based on what we just said and we know, we want to reduce this or get rid of it. So, starting again, it says to reduce the effect of bias current, a compensating resistor called RC is connected in series with a non-inverting input terminal or non-inverting terminal of the amplifier. RC must provide a DC path to ground. So, if a signal is capacitor coupled to the input, positive input or the non-inverting input, RC must, and RC here now is a compensation resistor, right? RC must be connected between the non-inverting input and ground. We will presently show that the proper choice of RC will minimize the offset voltage, the output offset voltage due to the bias current. So let's look at figure 22 here and see what's happening. So you notice what I have done here? What I have done here is ground both inputs. And we know that when you ground both inputs, there's no input voltages. No input voltages is going to, of course, result in theoretically no current at the input of the operation, both inputs of the operation amplifier. Is that correct?
Yes,
No
sir.
voltage, right. But, ladies and gentlemen, what we know is because of the activities that are going on in the movement of electrons resulting in current flow inside of the amplifier across the junction of the amplifier, resulting in voltage inside of the amplifier. That voltage is going to be amplified even when these two inputs are grounded to give you output voltage, which is our output offset voltage, right? Now, that voltage is going to cause a current. Remember, I don't have any input voltage, right? But that voltage is going to cause a current to flow. And that current, of course, is going to be a feedback current. That feedback current is going to come here. And that feedback current coming here. Remember what this point is called?
Virtual Earth.
Virtual ground. All right. So virtual ground would be the same as real ground. Agree? So if you have a current, that is going to be here, right here, that current is not going to go. That current is going to be available right here. And if that current is available right here, that current is available right here as well, which is going to be on the, and what? On a non-inverting input, because this is ground and this is virtual ground, eh? So the same current is going to be available on both. That is the current that is being fed back. Right? Because of the virtual ground concept. So the only difference is that this current, and I call it IB because it's what? It's a bias current, right? That current is going to be on the positive negative input, which is what is called IB minus, and it's the same current that is going to be on IB plus. And IB plus will show that it's on the non-inverting input. Good? But here, what we're doing is we're now putting up a resistor, a new resistor called a compensation resistor, on the input of the non-inverting input. Let's see what does that resistor do. Okay. So we will presently show that a proper choice of the value for RC will minimize the output offset voltage due to the bias current. Figure 1022 shows that the bias current, IB plus and IB minus, flowing into the positive and the negative, or the non-inverting and the inverting input, of course, of the operation amplifier. When the signal inputs are grounded, so there's no voltage that is being applied here, but we are realizing that because of an output offset voltage, current is flowing, coming back here to virtual ground, to ground, which result in IB being present at both inputs, right? IB, which is your bias current, your input bias current. So, although the bias current may actually flow into or out of the terminal, depending on the type of input circuitry, we will, for the sake of convenience, assume that the directions are shown and the values are always positive. Okay? So in other words, they're saying the current can either flow this way or that way. Okay? By assuming that the current value is positive. These assumptions will not affect our ultimate conclusion. The figure also shows the compensating resistor RC connected in series with a positive terminal. Note that this circuit applies to both inverting and non-inverting configurations. So now we're going to start to up the ante now. You guys have to follow me now. We have a couple more minutes before the time. So you have to follow me now, the equations. As a figure 1023A shows the equivalent circuit of figure 1022. Remember figure 1022? Just the operation amplifier, no input voltage, with our feedback, and we have input currents that are coming. Now, figure 23A is this circuit here. And what we're doing really and truly is having this part of the circuit remain the same as before. And then we're converting we're making this part of the circuit a little bit different. Now, if the current was flowing, ladies and gentlemen, this current that's coming here, virtual ground, go here or go here. If the current was flowing this direction, you agree with me that a current flowing IB minus that is flowing across R1 is going to result in a voltage. You agree with me? So
Yes, sir.
Yes, sir.
So we're going to have a voltage here, and likewise, we would have a voltage. Because of the fact that we have a resistor here, called a compensating resistor, we would develop a voltage across here if the current was also assumed to be flowing in that direction. And it doesn't really matter because current flow in terms of direction is all depends on, of course, where we determine to take our reference to. So that's what this is saying. So in other words, we can actually create voltage sources right here because this is going to be IB minus times R1 and IB plus times RC. So in other words, we can create two voltage sources, which is what is done here. Notice the currents now. So what we have is R1 and this is IB1, RC, IB plus and minus, and then IB plus. Now, because of that, we could shift that over to here and say that, okay, as I mentioned before, we can now call this a voltage source because it's I times R, right? So that's why we introduce or incorporate right now, right here. Even though we didn't have a voltage before, you realize we didn't have a voltage, it was grounded, right? But because of the feedback, now we have a resistor, now we have a voltage because the current is coming this direction. And that current, remember, is IB minus. So IB minus times R1 is going to give us a voltage of IB minus times R1. Agree?
Yes, sir.
Okay. And the same would be true for the non-inverting input. That the voltage source, that there could be a representation of a voltage source as well, because it's IB plus times RC that's going to give us a voltage source here. So now that is the case, we can then look at how it is that we can now that we know the bias current and we know the resistor, we know that there's supposed to be a resistor, we can then try and find how we can actually mitigate against this voltage that is being outputted in order to minimize this output voltage, which is our output offset voltage. Now that we understand that, let's go back a bit. So I said in figure 1023, it shows that we have the sources. I won't go back through that too much. But what is important is that if we look at figure 1023B, which is this one here, you'll agree with me that VO1, which is the voltage that has been applied to, this is input 1 and this is input 2 now. All right? So VO1, which is, remember now using superposition theorem, right? It means the output voltage of this network based on the voltage that has been applied at the input voltage 1 is going to be, remember, voltage is what? Gain times, the output voltage is going to be gain times what? The input voltage, right?
Yes, sir.
Yes, sir.
Output voltage, right. Now, what is the input voltage? If we look at this figure, the input voltage is going to be IB minus times R1. We established that already.
Yes, sir.
Good.
That would be
That's right. So it means that the output voltage due to this input now is going to be, see, VO1 is going to be what? This is what again? Oh, you guys are thinking now. That's why I said bear with me. What is this again? What is this?
that's
The voltage source, sir.
That's going to be the input voltage, right?
Yes, sir.
Yes, sir.
So the input voltage, VI, and if we're looking at, if we want to find what individual voltages are going to be at the output, you know, we'll have to ground this input, right? I use superposition, right? So,
Yes, sir.
right. So we're saying that doing that, grounding the input and a positive as a non-inverted input, and applying this one, we're going to get VO1. And that is going to VO1, the output voltage is a gain of the network times input voltage. We know what input voltage is. It is I minus B times R1. And what is this again?
Gain at the inverting, sir.
Gain, because we're gonna be, because this is grounded and this is a voltage that is now swapped to be developed on the input of the inverting input. You're gonna realize that this is now gonna be an inverting amplifier, right? So therefore, VO1, as the output voltage due to what's happening on this input, is gonna be this. Remember about this now, because you know what this is. It's gonna be equation 1041. And similarly, ladies and gentlemen, when we ground R2, sorry, when we ground this one now, R1, and apply, and then we're looking at doing the analysis. We want to see what the output voltage again is going to be due to this. We see that this is our input voltage. Yeah? This is our input voltage. And we know the output is going to be the input voltage times the gain of the amplifier. But if this is grounded and this is what we apply our input, we know that this network is going to be what? A non-inverting amplifier.
Yes, sir.
Yes, sir.
So therefore, the output for this network, the output voltage VO2, is going to be the input voltage. So the input voltage here. Yeah?
Yes, sir.
So it's the input voltage times the gain of the amplifier. And the gain of the amplifier is?
1 plus R4.
Right. So all of these we have proven so far. So now we have two voltages, VO1 and VO2, that is going to equate to the overall output voltage of a network. But before we go there, you realize that equation 1041 can be simplified.
Oh, yes,
R1
sir.
can cancel out.
So with R1 canceling, we're left with minus IB minus times minus RF. Yeah? Which is going to give us this. So that's our voltage due to V1, are based on this network. A question for you though. Why is it that we have minus I, why do we have a minus here? Because we have this as a gain as a minus already. You know? Why do we have a minus here?
Because we're considering the direction that the current moving.
We're assuming the current is going in this direction. And likewise, for this one, we're assuming the current is going in this direction. So that is why we're going to have, again, even for the non-inverted amplifier, we have a minus right here. Because the current is going in the opposite direction to what we're thinking how it should go. That's why we have a minus sign.
So even the polarity of the battery, sir. You see how the
Good.
negative at the top?
Good. So here, ladies and gentlemen, we have two equations. So we can now superimpose these equations. This plus this. And that's what's going to give us, remember, we have a superimpose to get what the overall output is going to be, right? Which is how we arrive at this equation, equation 1043. See that? We have this equation, which is this part. Yeah? See it? And then we have this part of the equation, which of course is this, which is now positive. So we say that combine equation 1041 and 1042, we obtain the total output offset voltage due to the bias current, which we designate as, notice the designation now, this is the output offset voltage, VOS. We put in bracket IB, because this is a bit, we're not talking about the bias current. So this is the total output offset voltage. That's the voltage of the output now. Due to the bias current is going to be this expression. So everybody have seen how I came up with equation 1043?
Yes, sir.
Yeah, man.
Cool. Not so hard after all, right? You have it in your own. I look kind of, you know? All right. So here's what's happening now. It said depending on which of the term on the right side of the equation, so depending on which one of these terms is greater, VOSIB, which is the output offset voltage due to the input bias current, may be positive or negative. So if this is greater, then obviously the voltage is going to be negative. If this is greater, then it's going to be positive, right? If this is greater than this. However, the sign, remember for voltages, what happens? However, the sign of VOS is of little interest. It doesn't matter whether or not it is where we decide that our reference is. Because remember, negative of a voltage all depends on where we're looking at our reference, right? It doesn't matter what our reference is. It doesn't matter. What matters is that we still have it, eh? Because a negative offset voltage is just as undesirable as a positive offset voltage. Because remember, what we want to do is to get rid of it. We want to get rid of the offset voltage. We're not business whether or not it want to be negative or positive. All right? Our real interest is to find a way of minimizing the magnitude of the offset voltage, offset output voltage due to the bias current. Towards that end, let us make a reasonable assumption that the two inputs are closely matched. So in other words, we're saying that, remember we saw that IB minus and IB plus, because we assume virtual ground, we can assume also that they are also equal, right? So it says that, consequently, we can say that IB plus actually equals to IB minus. Remember, the plus and the minus, it just means that the currents are on the different and the inverting and non-inverting terminals, right?
Yes, sir.
And if that's the case, let's call, if they're equal, or then we can say, okay, let's call it IBB. So wherever IB plus and IB minus is in this equation, we're going to call it IBB. So we're going to put back IBB here, IBB here, because this and this are equal. That's the assumption. So that's what happens. That's what makes this equation now become this equation. So what we have is that IB, when we do that, we can then factor out IB, right? IBB. So IBB, we can just do it one time. IBB times RF is this same one. So that's why we have this. And IBB, taking it out and put it out front. We don't have no more IBB. We have this expression. That's why we have equation 43 becoming equation 1044. Now, ladies and gentlemen, what are we trying to do? We're trying to get rid of VOS, which is what again? VOS is what?
Offset.
Output voltage. And in this case, due to the input bias current. So if we're trying to get rid of this, we want this to really become zero. If we want this to become zero, what do we do in this expression to make this become zero?
IB equals 0, sir.
Okay, we can do two things. We can see if the expression enclosed by the bracket 1044 in this bracket, we're equal to 0. So if we can make all of this that's in the bracket equal to 0, make this become 0. So if this becomes 0, IBB can become 0 because IBB is coming back already. Remember, IBB is something that is real. It's a current that is coming back, eh?
Yes, sir.
Right. So once you have the transistor functioning, your current cannot become 0 because it is the movements of electron internally. And that electrons result in your output voltage, offset voltage, which is going to be fed back. That's how we remember, that's how we got IB plus and IB minus, right? So if that's the case, this term cannot become 0. So it must be this term that becomes 0 to make this become 0. So if we equate this to be 0, so if we say RF minus 1 plus RF over 1 times RC equals to 0. If we equate this to be 0, then you realize we can find the value for RC. Because remember what RC is? RC is a compensation resistor that you're putting in a resistor that you're trying to use that resistor to make your offset voltage become 0. So from this expression, we can then find a value for RC. So we make RC being subject of the formula, and that gives us equation 1045. That RC, if you juggle this equation, ladies and gentlemen, you realize that RC is nothing more than the parallel combination of RF and R1. Okay? And this is easy maths. Easy maths. Bring this part over here at the equation. And then, of course, if we bring it out of the equation, we expand that part and then we make RC the subject of the formula. And you will see that RC becomes RF times R1 over RF plus R1. Remember what RF is our feedback resistor, right? And R1 is our input resistor. So we're saying if RC is the parallel combination of these two, then it means that putting that parallel combination of these two for RC right here, it is going to eliminate our output offset voltage. That's exactly what is being done right here. Because here's what's happening. If you put RC as a parallel combination and put back that into the equation, remember? Put back that into the big equation. Put RC being RF parallel R1. Put that back into this equation. And let me erase some of these. I know that our time is finished, but I want to catch you guys while they're fresh. So if we put, if we make this in this expression, if we make RC RF R1 over RF plus R1. Then we're in business. Okay? Expand this and see what you get. And expanding it, this is what happens, ladies and gentlemen. And they have done it for you. So we put in back, we put in RC back into this expression. And this is what happens. It gives the equation 1046. If that's the case, then this equation becomes very simple. So remember, putting back it in this at least not in this expression, this expression. Let's put it back in this expression. So put in RC here, and though it doesn't really matter. But put in RC as RF parallel, which is RF times R1. That's what RC is. R1 over RF plus R1. When we put that in the expression, we're going to get this equation. And when we get this equation, ladies and gentlemen, you see that this cancels this, and this cancels this. So what are we left with? We're left with everything that is in the bracket here is only RF that is left. So we're going to have IB minus RF minus IB plus RF. So we can factor out RF out of this, what remains. And what does that tell us? What does it tell us really? Are you guys still all there?
Yes, sir.
Okay. It says equation 46 shows that the offset voltage, remember VOS, due to IB, the offset voltage is proportional to the difference between IB plus and IB minus when RC is equal to R1 parallel RF. Because the inputs are usually reasonably well matched, the difference between IB plus and IB minus is quite small. The equation confirms the fact that the output offset voltage is 0 if IB plus exactly equal to IB minus. So you see, if these two are the same, remember I said that they are almost equal. If these two are the same in bracket, then if this is 1 minus 1, any variable minus itself is going to give you 0, not true?
Yes, sir.
And 0 times RF is going to give you 0. So that is what we're saying, is that the equation confirms the fact that the output offset voltage is equal to 0 or 0 if IB minus and IB plus are equal. So the output offset voltage due to the bias current may be either positive or negative depending on whether or not IB plus is greater than IB minus or vice versa. Unless actually measurements are made, we really know which current is larger. So a more useful equation for equation 4.6 or 46, rather 1046 is this. Take the modulus. Now the modulus of the output offset voltage due to the bias current is equal to IO RF. Now, what is IO RF? So we're bringing a new term, IIO RF is RF already. That is there. So we're saying that we're bringing this term as IIO. And IIO is really the modulus of what's in the bracket. So it doesn't matter if the two terms are the same, then it's going to be IIO is going to be 0. And if one is greater than the other, then it means that we're going to be having a little bit of voltage, which is due to the difference between the two. Which is why we have equation 10.7. So what this is telling you overall is that if the input offset current is given in the manufacturer's specification sheet, which is IB plus, that's what the manufacturer is going to give you, right? So if they give you this, you can actually use equation 1047, which is right here. Shows that the output offset is directly proportional to the value of the feedback resistor. For this reason, small resistance value should be used when offset is a critical consideration. However, to achieve large voltage gain, when RF is small, may require impractical small value resistor for R1. All right? To the extent that the amplifier may load the significant source driving it. Which simply means that, guess what? If the value for R1 is too small, the voltage. I'm getting a feedback. Somebody have the mic up. Right. So what happened is that another common manufacturer specification is called this simple input bias current, which is IB. It refers to either or both IB plus and IB minus. By convention, IB is taken as the average of both IB plus and IB minus. So what I do is just call IB, which is what is given most of the time by the manufacturer, the average of the two. So if they are the same, it's going to be 1 plus 1 divided by 2, which is going to give you 1. Right? So if they're the same. So IB is really the average of both. And I say IB is typically much larger than IO. And of course, it must be larger than IIO. Remember, IIO is what? The difference between the two, eh? Well, IB is this average of the two. Because IB is on the same order of magnitude as IB plus and IB minus, while IIO is a difference between the two. It is important to know that IIO is normally given by the manufacturer as a maximum value, meaning that it can actually be between 0 and the published value. Therefore, the term VOS IB equals to IIO RF should be taken as a maximum or the worst case value. Next time we meet, we're going to look at the example. So I can put an X here because you should know, asterisk, you should know, be able to take all that we have looked at to solve, well, it's solved for you, but to actually approach this question. All right? And if you do not understand, then you can come with your question to say what you don't understand about the solution due to what we would have done before. So the next time we meet, you're gonna come, a matter of fact, we're not gonna look at it unless you come to me with question. If you come to me with question, it means that you would have looked at it and don't understand. If you don't come to me with question, it means that you would have looked at it and you fully grasp what was being done right here. Which means that we move on to the other thing. Remember I said that there are two things that you can use to minimize your output offset voltage. What manufacturer will give you? They'll give you the input bias current or your input offset voltage. So next time we meet, we're going to look at what the input offset voltage is and how we can use it to offset or minimize the output offset voltage. Am I clear?
Yes, sir.
All right. Wonderful. Let me see how many people I still have. All right, for everybody. I just saw Mark register, like some of my colleagues say, them marking register and them doing that and doing. I don't have time for that, You guys are adults. If you come to learn, you come to learn.
He's right, sir.
You don't want to learn, and you don't want to get by. That's fine. A lot of people are saying, boy, we need to be doing video. Just make sure that you're actually in class. And we're seeing that you're in class instead of just opening your joining the session and just put your mic on mute and go on about your business. As if I don't have anything to do. I really don't care. That's not my business. If you want to do that, it's up to you, no? Right, Delroy?
Batch it dead, sir.
Like Delroy God, man. Delroy watch it God.
Like a good while gone. You look like in the drawing box, sir, but I guess that did too.
So, sir,
Yes.
when you push out the recording them, sir?
Over this weekend. I have time. Actually, tomorrow.
All right, sir.
You remember we have a date with Destiny next week, right?
How would that go, sir?
We have a test next week.
Which day?
Today?
Sir, you couldn't put it in the other week, sir.
Mm-hmm. What you want in another week?
Oh wait, sir, can you tell us the topic? Stop coming on the test, sir.
Everything we do so far.
Okay, very enough.
Sir, how are we doing it, sir? The first half of the class or the second half?
I would suggest that we do it the first half of the class. But I'll give people enough time, so I'll start probably because I know that a lot of people don't join on the dot at 5 o'clock. So I'll probably give people 15 minutes. And it joins. So after 15 minutes, nobody got no excuse.
All right, sir, no problem.
Spread the word because I know that some people are still gonna come here.
Upshutter is back.
I don't know. We didn't know that we were going. Even though I put a message in the chat or in the class, but believe it or not, students are always very uninformed where assessment is concerned. You know, for me, when I was going to school, and I tell you guys this, and you probably figure more or less that probably I'm weird. I really didn't mind if I get a test every week. You know why? Anybody can tell me why?
Reinforcement,
Yeah,
sir.
genius, sir.
You were very smart.
No, it has nothing to do with me.
Knowing what you know from what you do.
What it does is that it gives me an opportunity to stay on point. So what it means is that I will be very I'll do what it takes in order to ensure that I am locked on to knowledge. And when I get a test every week, it then reinforces what I know, or it tells me what I do not know properly. Because sometimes you think you know some things, But it's only when you go and you realize that, you know, when you do the assessment, you say, oh shit, I really did not know this thing out. Let me then see what I have to do or the work I need to put in. But sometimes when you leave it for too long and you get it all at once, you come to the session thinking that again, you know. And then when you probably see the questions, you said, you know, at that time you regret the fact that you actually discovered at that time that you really did not or was not very clear on some of the things that you're doing. I know that, and you guys can tell me your strategies. I know that back when you were having in class face-to-face session, one of the things that you guys did, and one of the things that I heard that you guys did was, you know, was to have group sessions or group studies. Now that you don't have that, what do? Do you guys still have sessions, meet online and have sessions of such?
Sir, they can any recording and we'll have a discussion, sir.
All right, let me do that.
Sir, where did you say you posted that the test was next week?
No,
Where did I
don't
post
it?
I didn't post it yet. I just inform you.
Oh,
But what
okay.
I'm saying is that I'm going to post it because, and I'm asking you to share the word.
All right, no
Well,
problem. What is the format?
You know, I haven't done the test as yet, so I can't tell you the format. Just come prepared to do the test. Usually, like what I did with devices one for those who did it with me, you find that you probably have a combination of all different types of assessment. Multiple choice, short answers, and of course, you're gonna have answers where you have to do your calculation or whatever your case is and upload.
What platform will this be on?
Right here, Google platform. It's gonna be posted, right? Just like how I post the notes. It's gonna be posted. You're gonna see the test. I tell you when. I'll post it when you're supposed to start. You'll be having access to it. You'll do the test. It's like an open book test, you know. But guess what? You gotta be careful. You gotta be careful because you're gonna be having time constraint. And the amount of time you spend to try to find information, time might be against you. And if you do not upload, and actually it's gonna be much more serious than the last time, ladies and gentlemen. Because now you're seasoned campaigners. If you do not submit within
Sir,
the time,
I'm not seasoned. I really am not.
you're not seasoned.
From now, get a photo to PDF convert on your phone, so you can.
Yeah, I just download Adobe Scanner tonight.
And another thing, you'd rather want to like send them into our WhatsApp and then download them through WhatsApp web on your computer, so you can get them on the computer faster than having to. Like, that's the fastest way we know so far. Or you can submit them directly through Google Classroom on your phone.
All right then.
Which goes back to the question I'd asked. Let's say I should start the recording. How do you guys actually do it? Because I know that learning has been affected in a massive way. In not to incorporate the in-person class. But how do you guys do it? You guys still have ways and means of touching base. I know that there are a lot of WhatsApping and various types of groups and group chats and all
Yes,
that.
that's just it, sir. If somebody has a question, I'm just asking the group, sir.
I didn't hear that, Mr. Vaso. What was that?
When someone has a question, sir, they just ask in the group and we help.
Okay. Well,
Not really.
as far as I'm concerned, whatever it
Don't
takes,
really
it's
practice as
important.
much.
Now, let me tell you why. There is no I in a team, as you have heard a lot of times people say. But engineering, and especially when you go out there to do the real engineering work. When you're employed and things. Remember something that you guys are gonna. This is something that you guys are gonna have to come to the board fast with. You're not an engineer when you finish after 4 years. You're a graduate engineering student who is now going to be working to concretize theory with practical to become that hardcore engineer. Do not believe that you're going to take your certification to a company or to some company and then thinking that the certificate that you would have gotten or your certification that you'd have gotten is of any interest to the people who are looking to employ you. All that certification does is that it provides you with the technical capabilities, knowledge, and give you what it takes to knock on the door very loudly or sometimes kick the door down for people to employ you. You're going to have to go and show them that you actually bring something to the table. Or there's something that you have potentially that you can bring to the table to help them to achieve their company's goal. I've gone to several interviews. I've sat on several panels where people believe that they come in with a honors, first class honors or whatever, and you have a degree and you're no Mr. Macho Man or you're this bright girl and you're coming into to do what? You're coming into an organization basically to plant your own foot, to stand up and to try to stand on your own. And in the process, in doing so, you're going to be trying to help the organization by learning quickly on your feet, adapting and applying what you would have learned in the classroom to industry, to try and help the organization to achieve its objectives. Do not go there thinking that when you get your certification, that's it. You're now probably the only person or one of the few people who might be going in at that level with your degree or whatever certification. That's not what employers are looking for. They're looking for somebody who is willing to learn, multi-talented, and have the right attitude and aptitude that can help to contribute to consistent development of an organization. And I have this little discussion right now because students believe sometimes that on their own they can achieve the thing, and by achieving this thing in terms of having their certification, they are